Hello my friend, I'm going to record a video for your simulation. I've sent you the results about voltage and copper losses and the load. Now I'm going to tell you about the changes I've made in your simulation. I've listed the changes to go through from the list. First of all, I don't remember what boundaries did you use, but I've used region from this key. I've used region that I've hide for active view. The region is covered all the parts a little bit bigger, and let me make it visible. Now we can see it. Okay, the region is a little bigger and it doesn't need any boundaries or assign boundary. In 3D model you don't need to assign any kind of boundary or insulation. The biggest part of the simulation will be considered as zero potential axial potential. It would consider as zero, and you don't need to assign any boundary. The second part is change in core material about loss and conductivity. The core material that you used was the material that you assigned here. I didn't change the loss coefficients, but and you used an BH curve for your material. If you need to change a material, you can use the default materials of the software, like steel 1008 or steel 1010. But if you need to change the material BH curve, you can change it right here. The thing that you should consider is bulk conductivity. Bulk conductivity should be zero when you use laminated steel. The laminated steel doesn't allow the focal current to begin, and we laminate the core to eliminate the focal current. So if you use lamination, like here in transformer, you have to set the bulk conductivity as a zero, and the losses that consider the core loss should be assigned here by the coefficients like KH or KC or KE that represent the DC flux loss, eddy effect from flux loss, and I don't remember these two. You can go to help and see the coefficients, but if you want to use another core or calculate the core loss, you can come here and click on core loss at one frequency. I think you assigned it yourself, so you are familiar with this part. You can assign B as a Tesla and power loss in kilograms to calculate the core loss coefficient. Okay, now let's go to the third part, change in primary and secondary winding. You imported the windings from, I don't know, AutoCAD or SolidWorks. These softwares draw the circle very fragmented way. They draw it a circle completely as a circle, but here in Maxwell, because we need to mesh the geometry, it's better to draw the circle parts by the software itself. I've deleted the the winding that you imported, and draw one of them myself. It's a cylinder here that subtracted from another cylinder. It's very easy to draw them. I use the cylinder part. If you need any help here, I can illustrate the drawing the parts, but I know you're good at it. I've drawn the winding again and change in copper conductivity. Okay, it's very important. This part is important. You know the geometry that occupied by the copper here. Okay, for example, 800 turns for low voltage winding, and we draw a cylinder like this, but the effective copper area is much less than this area. We assign the winding to a sheet here like this, okay, but in real transformer, in real world, the copper doesn't occupy the whole of this area. So if you use bigger copper area for your winding, of course your copper loss will be less, because the resistance of the winding won't be as much as the real transformer. So in help of the software, it's illustrated to it told us to, if you know I've asked you the resistance of the primary and secondary winding. For example, you told me that the secondary winding, the low voltage winding, the high voltage winding have let me see, 688 milliohms. Okay, so if we inject a current with a DC current with 1 ampere, so we should see the copper loss. The copper loss is represented here as a stranded loss. Okay, a stranded loss R. A stranded loss. The copper loss is presented here with a stranded loss. So if we want to see the real copper loss, the resistance should be as much as the resistance of a real transformer. So I injected 1 ampere current in another simulation. I injected 1 ampere current to one of the windings and run the simulation and get the results of a stranded loss. Okay, the stranded loss that showed me in that simulation was I wanted to see 688 milliwatts for copper loss, okay? But the simulation told that the copper loss in this area of the winding, in this area of the copper winding, is 489. So I have to increase the conductivity to get the real copper loss. I've used this coefficient to correct the conductivity of the winding. I've done this simulation for low voltage and high voltage in separate simulations and corrected the conductivity by these coefficients. Okay, I hope you got what I meant. If you have any question, don't consider to ask. I am always online. Okay, change in copper conductivity, I told you, HV and low voltage excitation. In the simulation that you sent to me, you've excited both sides of low voltage and high voltage. In real world, you can't feed low voltage and high voltage in the same time. You feed for example, high voltage and connect the transformer to the low voltage load or anything. When you use high voltage and low voltage excitation in the same time, the flux can't go through the cores correctly because the flux is related to the voltage. So if you want to excite the transformer, just excite one side and use the other side as a load. I've excited the high voltage winding. The voltage type excitation, the resistance is 688 milliohms, and for the getting faster to the steady state, I've used a conditional type for voltage. I copy the conditions here to illustrate. Okay, the condition that I've used is this. I wanted to excite the high voltage winding by this part via peak cross cosine 2 cross P cross the frequency cross the time. Okay, I wanted to use this as in a steady state, but I wanted to excite this winding little by little with a ramp. So I've crossed a ramp here. The type of excitation with if is like this. If the condition colon, then if this condition is true, it would execute this part, else it would execute this part. Okay, condition, then else. If time is little than 0.1, the voltage would be like this: 10 cross time cross this part, the voltage, the cosine voltage. It would it would make the voltage like this. The steady state voltage would be a cosine with the VA peak amplitude, okay? But when you cross the ramp at it, it begins with little voltage and you don't see the inrush current, and you don't need to stay or simulate lots of time to get to the steady state. It would start at the steady state. So I use this trick to make the simulation steady state very faster. Okay, I use if time is less than 0.1, like this. The excitation would be a cosine type cross a ramp, and if time is bigger than 100 milliseconds, the excitation would be a complete cosine. Okay, I excited the HV or high voltage winding with this condition and connect just a load to the low voltage side, or I can excite the low voltage side and connect the high voltage side to a load. But in reality we use low voltage side as a load. Or if you want to connect it to the grid, you have to consider the phase of the voltage and phase of the grid. But I've connected it to a load. I've calculated the load that gets about 12 megawatts. It was 9.7 ohm, and it's the resistance of the low voltage side that I've added here. Okay, so I've excited the low voltage just with the load. HV and LV excitation, load assignment, I told you about its linear voltage excitation. I told you with this condition. Mesh operation. If you use little and precise mesh in 3D model, it would take a lot of time to simulate the simulation, but I've done this like this. I've selected all the parts, I've assigned the mesh operation, inside selection, and length spaced. Okay, I've done it, so I have the mesh operation here. I've assigned the maximum length of element as 50 millimeter, but I restricted the total number of mesh as 80,000 mesh because my computer took more time to simulate if the mesh was very high, but this mesh operation is enough. I believe it's very good here, but if you wanted to, it's very good in many papers and journals. The mesh are much bigger than our mesh, but if you wanted to make a more precise simulation, you can go right there and make a mesh more precise. You can lower this number and make this number higher to get a better mesh. Mesh operation analysis setup. Okay, in analysis setup, I've add solution setup here. I think you did that too. And the step time that I've selected was 500 microseconds, and it's good. It would have about 40 steps in a period of sine wave or cosine wave. Here is the analysis setup and getting results and fields. You can come to the result, create a transient report, rectangular plot here, and I will check all the things that we have. In winding, if you want to calculate the L, the mutual inductance, you have to set it at the beginning of the simulation. It would set, I think, let me see, it would set at a matrix computation, compute inductance matrix. You should make that box checked for simulation the L, but we don't need L in transformer here. You can see the flux linkage. It's the flux linkage. It's just like the voltage, but the flux is Weber. The other result that we take is input voltage in all phases. You can see the input voltage and currents of all phases and windings. In loss, you can see core loss that, for calculating core loss, let me say that for calculating core loss, you have to come to excitation in core loss, set core loss, and check this box for the parts that you want to calculate the core loss. I've checked this for my course, so I have core loss here about 12 kilowatts. We don't have any solid loss here. Solid loss is calculated in the parts that eddy effect make a loss. We don't have. A stranded loss is primary and secondary copper loss is about 20 kilowatts, and the stranded loss R would calculate the load of this R. Stranded loss R means the resistance of a stranded would be calculated. It is I believe I said it's about 12 megawatts. Okay, so what we have in the other parts in your simulation, we don't have moving or rotating like electrical motors, so it's all about the results that you can get, and we can get field results like this. You can right click on the project, go to B vector. When you select the B vector and click on done, you should select the time that you want to view the field. I've just saved the field in the last second that I've simulated. It's here, but if you want more fields to be saved, you can go to setup analysis. In save field tab, you have to select the times that you want to save the field. I've selected these times, but I didn't simulate the project until this because it's got to a steady state part and I've aborted the simulation. But you can select, for example, from 100 milliseconds to 120 milliseconds and replace the list. It would save the field in a steady state. I don't save these changes because I want to send the simulation with results for you. And here the B part, you can see the flux that's going through the legs of the transformer. I've simulated your simulation in 3 files with current, voltage without that ramp part, and this with the voltage with ramp part that gets a steady state sooner. The whole folder is, let me check. The whole folder is 2 gigabytes, but in simulation that I've used the ramp, I didn't save the field, so the whole simulation is about 200 megabytes, so I can compress it with WinRAR and send the result for you. Thank you for your cooperation. I hope hear from you more and more, and if any of your friends or university students want any project, I will be glad to cooperate. And you yourself, if you have any question, I would be glad to answer anytime.